So we ended with a derivation of light as a wave. So we can say that the electric field, okay, some amplitude times sine kx, it can be plus or minus, do minus, because that, if you remember, that corresponds to a wave moving to the right. And then B equals B naught sine kx minus omega t. And again, remembering what we had from waves from physics 1. So in physics 1, wave y equals y naught sine kx minus omega t. So that defined a wave here. We said that k was related to the wavelength. K was 2 pi divided by the wavelength. Omega was 2 pi times the frequency. So that's the same as 2 pi over the period. Frequency is 1 over period. Well, if you think about it, there's a relationship between period and wavelength. So in the time that takes this peak to go down and back up, that's the same as this moving over to there. So we would say the speed is going to be equal to the wavelength. So there's the wavelength right there, divided by the period. Well, that's going to be the same as wavelength times frequency. So C equals lambda F, basic relationship for waves. Again, this should all be familiar to you from when you saw waves in physics 1. Okay, so that's just a repeat right there. Well, let's go back to light. So we know that partial of E respect to X equals minus partial of B respect to time. And so if we take the partial of E respect to X, remember E is E naught sine kx minus omega t, and B is some B naught sine kx minus omega t. So partial of E respect to X, so take a derivative of E respect to X, then that's going to be E naught. Derivative of the sine is the cosine. So cosine kx minus omega t, but we get a k out in front. That's equal to minus derivative of B. So we get B naught, okay. Derivative of the sine is the cosine. So cosine kx minus omega t, we get a minus omega out. So that minus makes that minus a plus, and we get an omega. Those two are both on the same side. And so we look at this and we say, well, wait a minute. E naught equals omega over k B naught. Well, omega over k is equal to the speed of light, c, the wave speed. So that means E naught equals c B naught. So in a light wave, you have simultaneous electric and magnetic fields, and they are related to each other precisely as E naught equals c B naught. And so they're perpendicular to each other. We saw that they have to be perpendicular to each other because the fluxes are perpendicular to each other. And so an electric field creates an electric current, and so the magnetic field is always perpendicular to that, so it's going to be perpendicular to the electric field. And so what we can imagine is we have light, and the light might be an electric field, so we have an electric field like that, and so the electric field's up here, down here, up here, down here, up there. The magnetic field is perpendicular to that. So where the electric field is up, the magnetic field is out of the board. Where the electric field's down, the magnetic field is into the board. Where the electric field's up, the magnetic field's out of the board. Where the electric field's down, magnetic field into the board, and so forth. So that corresponds to light moving this way. If light were moving to the left, then these would all be into the board, that'd be out of the board, that'd be into the board, and so forth. So it'd be the other direction if light were moving in the other direction. And so with that, we can now define this basic property of light. All the other stuff that you talked about with waves in physics 1 also holds. So we have intensity of waves. So intensity of waves is just going to be the power over the area. So that would define intensity. And so we would talk about light intensity as being, so many watts per square meter. In fact, there's something called the solar constant, which is 1.4 kilowatts per square meter. And that is roughly the amount of solar energy, light energy, striking Earth outside the atmosphere. So it's a little bit less than that on the surface of the Earth, but again, outside the atmosphere, a one square meter solar panel would get 1.4 kilowatts of power hitting it, at least perpendicular to it. And so that gives you an idea. Now you don't get all that converted into energy, only some of that light, because that's all different wavelengths of light. And again, we haven't talked about that yet, but there's different wavelengths of light, what we call the electromagnetic spectrum. So in wavelengths of light, you can have short wavelengths, you can have long wavelengths. Your eye, visible light, sees a range of 400 nanometers to 700 nanometers. That's visible light. So this is the red end of the spectrum, and this is the violet end of the spectrum. And so the colors of light you see, if you had a prism, the colors of light that you see break up into red, orange, yellow, green, blue, indigo, and violet. Now, personally, I don't see a whole lot of difference between indigo and violet. It looks like blue and then purple to me. But Isaac Newton gave it these names right here. And so that's the visible spectrum. So this is 700 nanometers here. This is about 400 nanometers right there. Now, an interesting thing happened is that astronomer named William Herschel was studying this, and he got to wondering if maybe different colors of light actually warmed you differently, because you knew sitting out in the sunlight it would warm you. So he took a thermometer and he put the thermometer and moved the thermometer between the different colors of light to see which one made the thermometer get warmer. Okay, and he it turns out this is not a very good experiment, because he didn't know about how light was absorbed. But what he did do was, he got done, he set down the thermometer here off the red end of the spectrum, and he noticed that it actually got warm, which meant there was light up here that he could not see. It was less bent than red, and it was definitely there, and he was able to measure it. And so we call that light that's less than red infrared light. Well, another physicist later stuck a thermometer at the other end past the violet and realized that it also warmed up. And so we call that ultraviolet light. Now, you see 400 to 700 nanometers. There are other creatures on this planet that see other wavelengths. For example, bees and many insects see into the ultraviolet. A lot of migratory birds see in the ultraviolet, and that's useful, because that means that they can go about their business doing what they do, navigating by the sun on cloudy days, because ultraviolet light will actually come through the clouds. Pit vipers, rattlesnakes, copperheads, water moccasins, the pits on the side of their head pick up infrared light. So a lot of these are nocturnal hunters. So at night, they don't use their eyes necessarily to see. They use the pits on the side of their head to see infrared light. And then a small mammal like a mouse or something would be glowing in infrared light. And so they'd be able to detect in the dark. That's why a lot of people actually get bit by copperheads at night, is that's when they're out and about, and then you can't see them, and you step on them and they bite you. And so there are other wavelengths. So the range of light, it's all electric and magnetic waves. So we call this the electromagnetic spectrum. There's much prettier drawing of it in the textbook, okay, that you can look at. For the electromagnetic spectrum, the shortest wavelengths of electromagnetic spectrum are gamma rays, okay, and then we have X-rays, okay, and then ultraviolet, and then visible, okay, then infrared, and then radio waves. Really short radio waves we often call microwaves. And so that is the electromagnetic spectrum. And again, you can look in the book. It tells you a little bit more about the different wavelengths here that correspond to the different parts of the electromagnetic spectrum. Gamma rays, very, very short wavelengths. So they're again, 400 to 700 nanometers is visible light. Okay, ultraviolet light goes all the way down to around 200 or so nanometers. X-rays go down to like close to a nanometer. Shorter than that are going to be gamma rays. There's really short X-ray, really long gamma ray. There's not really much difference between them. So sometimes they say 0.10 nanometers, sometimes 1 nanometer. Whatever is convenient. Infrared light goes up, and again, long wavelength infrared is very hard to distinguish from very, very short wavelength radio waves, microwaves, and so the delineator in there is somewhere in the neighborhood of a centimeter or so. Okay, but that is the electromagnetic spectrum, so the wavelengths of light. And so all of that is light. It is all the same thing. It is all electric and magnetic waves. And so there we have it. So our next thing we're going to do is have a mathematical description of the light and the relationship of all this, but we'll have to save that for the next lecture.